Hello students, this is the section correlation from the chapter summarizing bivariate data. The objectives for this unit will be to construct a scatter plot for bivariate data, compute and interpret the correlation coefficient, and to understand that correlation is not the same as causation. I would like to start by refreshing your memory with the definitions of an order pair. An order pair consists of values of two variables for each individual in the data set, and data consisting of order pairs is called bivariate data, or are called bivariate data. We have covered several visual representations or graphical summaries of data. Today we're going to learn a new one, scatter plots. In a scatter plot, each individual in the data set contributes to an order pair of numbers, and each order pair is plotted on a set of axes. Think of the coordinates that you had to graph in the Cartesian plane in your algebra classes. Now, depending on the behavior of your plots or your scatter plot, we're going to be labeling our correlations as positive, negative, or no correlation. Sometimes it's very clear, like in the examples on your screen. Sometimes it's not as easily spotted. If you notice on the first two pictures, we have a positive linear and a negative linear correlation. If your graph looks like it's increasing from left to right, or if your graph looks like it's decreasing from left to right, is how we're going to label our correlation. If there's no pattern at all, we call that no correlation. But if it kind of looks like your graph is going upwards or downwards, we call it weak linear. Sometimes you don't have a linear correlation. Sometimes it could be a curve or a different pattern. Take for example the two pictures on the bottom. We have letter D to have a positive nonlinear because your graph looks like it's increasing from left to right, but not in a line form. Similarly, letter E, it's decreasing, but not in a line form. In this section, we're only going to talk about the linear correlation. Okay, so two variables have a positive association if large values of one variable are associated with large values of the other. Two variables have negative association if small values of one variable are associated with small variables of the other. I just spotted a mistake. Two variables have a linear relationship if the data tends to cluster around a straight line when plotted in a scatter plot. Let's take, for example, in our next slide, the price of eggs and the price of milk. I'm going to show you a table that represents the average price in dollars for a dozen eggs and a gallon of milk. The table represents the prices for each month in a recent year. This will be considered your order pairs. If we were graphing this in a Cartesian plane, think of the price of the dozen of eggs to be your X variable and the price of the gallon of milk to be your Y variable. We're going to plot them, but not in the Cartesian plane. It will be just in a graph. 1.94 will be paired with 3.58 and so on. Each one of those, the dozen of eggs and the gallon of milk, will be of order pair. This one will be one, this one will be another one, and so on. Then we're going to construct a scatter plot of milk versus the price of egg. Milk will be your Y variable. The price of eggs will be your X variable. Here's the graph after we plot the scatter plot. You can choose to be your axis, the range in your axis and the range in your Y to be whatever you want. In this example, we had the price of eggs to be ranging between 0 and 2.5, and each of our lines represented half. And the range from the price of milk in this graph, we just put it in between 3.35 and 3.6, and each of the the units were also half. Actually, it was 0.05. I'm sorry, 0.05. If you notice, it looks like we have a positive linear association or a positive correlation. In order to be more accurate, we're going to be using the correlation coefficient to determine how strong our positive or negative correlation is. Let's suppose we have a given order set of pairs, a given set of ordered pairs. We're going to have computed the sample means for both the x and the y variables. We're going to also compute the sample standard deviation for both the x and the y variables. And we're going to have a sample size n, which in this case was 12, for the count of the months in the year. The correlation coefficient is given by this formula. We're going to multiply 1 divided by 1 less than the sample count times the sum of the product of these two computations. We're going to subtract from each of our values the sample mean and divide by the standard deviation for the x, and then also for the other one, subtract the sample mean for the y, divide by the sample standard deviation for the y for each of your values. And you're going to compute, to multiply them. Okay, so first step, we need to know what are the means and the standard deviation for each, the price of the milk and the price of the eggs. I hope you remember from the previous chapters how to do this. If you don't, let me show you. I'm going to be using Excel to show you how to find the mean and the standard deviation. Remember, we're finding the sample mean and the sample standard deviation as per our definition. Okay, here's the price of the eggs and the price of the milk. I want to find the mean for the price of eggs. We're going to use the command average. You can just click on it, and we select all of the price for the X column. 1.83, and the mean for the Y will be average. Oh, sorry. Right here. 3.49. For standard deviation, remember we use the command stdev. Oh, wait, I forgot the equal. stdev. But I want the sample one point s for the x and then for the y. I got my values. And I know the count is 12 for each, the sample size. 1.20 was 0.122 and 0.058 for our standard deviation, and our means were 1.83 and 3.49. Okay, now let's create a table. If we're doing this by hand, this will be the steps we were going to take. You have to construct a column for the values of x and the values of y, and each of the computations you have to do before you multiply the values. I'm going to show you how to do the computation, and you have to skip, and you can skip all the steps in Excel, but first let me show you how the formula works. We're going to compute the values x minus the mean divided by the standard deviation for all of the x values, and then y minus the mean divided by the standard deviation for all of the y values. In other words, for my x column, I'm going to subtract from 1.94 the mean 1.8375 and divide by the standard deviation for the x values 0.122 for each one. And after I do it with 1.84, I'm going to do it with 1.80 and so on. That will be my next column. Some of the values will be negative because the mean will be greater than the price of the eggs. Then you have to repeat those steps with the y values. You're going to subtract from 3.58 the mean for the y values, which is 3.49, and divide by the standard deviation for each of your values, for each of your y values or the price of the milk. Here I already did the computations. Now, according to our formula, we have to multiply those two computations and then add all of those multiplications or all those products. Here's the multiplication of them. I multiply the first one times each other, and then the second one, and so on. I got that the sum for this last column was 9.28, 99, 65, 44, and it keeps on going. I just kept those decimal numbers. Then that sum we have to multiply times 1 over n minus 1, or if you want to see it like this, you can also divide that sum by n minus 1, or 1 minus the sample size, which was 12 in this case. I'm going to divide by 11. The correlation coefficient was 0.8445, if we want to round to the 4th decimal place. In Excel, we don't have to do all of these columns, and you don't have to do all this computation. To find the correlation coefficient R, all you have to do is use the command equals correl, C-O-R-R-E-L, open parentheses. You choose the first column, the one that is the independent variable in this case, press comma, and then select the second column, 0.8445. Again, you have to put equal, type correl, C-O-R-R-E-L, open parentheses, select the first column, then press comma. That's how before you select the second one. You type on the keyword a comma, and then select the second one. That's how you find your correlation coefficient. Now, if you're doing it by hand, please do not round the intermediate values you're going to be using to calculate the correlation coefficient. You can just round your final answer to 3 decimal places. In this case, it will be 0.845. Now, whenever we want to interpret the correlation coefficient, if R is positive, then the variables have a positive linear association. If R is negative, then the variables have a negative linear association. And the closer your value is to 0, then the weaker your linear association is. The closer your R correlation coefficient is to 1, then the stronger your linear association is. If it's positive 1, the closer it is to positive 1, it's a strong positive linear correlation. If it's close to negative 1, then it's a strongly negative linear association. Now, in the case you end up having exactly 1 or exactly negative 1 as your correlation coefficient, then the points line exactly on a straight line with either a positive or negative slope. And the variables have a perfect linear association. Positive if your correlation coefficient is 1, or negative if your correlation coefficient is equal to -1. Now, when two variables are not linearly related, the correlation coefficient does not provide a reliable description of the relationship between the variables. Again, the correlation coefficient only works for linear associations. If you have a nonlinear association, whether it's positive or negative, the correlation coefficient does not describe the relation appropriately. It's not reliable. Now, the correlation coefficient, I don't know if you remember the resistant definition. Remember, a resistant statistic, it can survive having outliers. It does not get affected by very large values or very small values in your data set. Well, correlation coefficient is not resistant. If you have an outlier, then the correlation coefficient may be misleading. And finally, correlation does not mean causation. It's not the same thing. When two variables are correlated, we cannot conclude that changing the value of one variable will cause a change in the value of the other. For example, if we decrease the price in milk, that does not mean it's going to decrease the price in eggs or increase it. The fact that one variable is changing, although they're correlated, does not mean the other one has to change. And just in case you hadn't taken notes, remember the command you're going to use in Excel or in Google Sheets is going to be Correl, Correl, and then you select both of your variable or cell columns for your values, for your variable values, separated by a comma. If you want to, you can practice finding this one in the screen in Excel or Google Sheets. And this is the command, if you're taking notes, to find the correlation coefficient, which represents the correlation between X and Y. Thank you so much for watching this video. I hope it was clear enough, and I hope I didn't go that fast because I think this is one of my shortest videos so far. Have a good day.